So we were talking earlier, and I mentioned that actually I don't consider myself much of an expert in spectral graph theory, more like an enthusiast. So I'm going to try and show a few things that I find pretty and interesting, and that will hopefully give you some sort of flavor what spectral graph theory is about, and how linear algebra and graph theory interact in a nice way. So let me share my screen. I hope you can see my slides now. So, of course, it's a vast area, and I'll really just stick to some small aspects of it. There would be so much more to talk about when it comes to spectral graph theory. I could certainly fill 10 lectures. But yeah, as I said, I'd like to give you at least a little bit of a flavor. I also don't assume any kind of familiarity with spectral graph theory, so I'll basically try to develop everything from scratch as much as possible. Some of the concepts, such as adjacency matrix, eigenvalues, and so forth, have already been mentioned earlier this week, specifically on Monday. But maybe some of you weren't there on Monday, so I don't assume familiarity with that either. So let me start. What are the key concepts here in spectral graph theory? Well, first of all, you start by associating matrices with graphs. So the most basic instance to do that is the adjacency matrix of a graph. And to define that, you need to first fix some order on your vertices. It's an arbitrary order. You can choose any order you like. And as it turns out, for the purpose of spectral graph theory, really any order of vertices will do. And then you define the entries of the adjacency matrix to be either 1 or 0, depending on whether or not your vertices are adjacent. So if vertex I and vertex j are adjacent, then you put a 1 in the corresponding entry of your matrix and a 0 otherwise. So here is a simple example, a 4-vertex graph with a 4x4 adjacency matrix. You see that there is a 1 whenever I have an edge, like v1, v2. There is an edge, so there are 1s in these places. There is an edge also between v1 and v4, so we put a 1 here and here. There is no edge between v1 and v3, so there and there you have zeros. In simple graphs, and I will just be considering those, I'm not allowing any loops and multiple edges. The diagonal will always be full of zeros because no vertex is adjacent to itself. So we have that as a guarantee. Our adjacency matrix is always a symmetric matrix with diagonal entries all 0. A second matrix you can associate with a graph is an incidence matrix. And so you also fix an order on the edges and define a matrix that's not a rectangular matrix where the rows correspond to the vertices and the columns correspond to the edges. And you put a 1 whenever the vertex is incident to the edge. So here v1 is incident to edges e1 and e3. So we put a 1 in the first column and the third column of row 1. And a 0 in all the other places in row 1 because v1 is not incident to the other 3 edges, and so forth. So that's the second basic matrix that one associates with the graph, the incidence matrix. Now you can already start doing some matrix algebra. You can try and investigate what happens if you manipulate these matrices, if you perform operations with these matrices. One thing you can do is you can take the incidence matrix and multiply it by its transpose. So you can't multiply it by itself generally because it's rectangular, so the dimensions wouldn't fit, but you can always multiply the incidence matrix with its transpose. And then it's not very difficult to convince yourself that the product always has two parts. The one is basically just the adjacency matrix, and the diagonal consists precisely of the degrees of the vertices. And that's because, you know, the rows of the incidence matrix, they correspond to the vertices of the graph. So if you take a row vector in your incidence matrix and its inner product with another row vector, then the pairwise products are most of the time zero, unless there is an edge exactly between those two vertices. Then I'm getting to multiply one by one, and that gives me a product of one, and the inner product of the corresponding rows is then one. If they're adjacent and otherwise, all the pairwise products I can form will be zero. So, for example, V2 and V3, they're adjacent by edge E2. So when I take these two vectors, they agree here in column 2. So there I'm getting a product of 1, but all the other pairwise products are 0. So the inner product of second and third row vector is 1. That's because they're adjacent. If I take two vertices that are not adjacent, V1 and V3, then you see that the two vectors are in fact orthogonal. If I take their inner product, all the pairwise products are zeros. So I'm getting 0. And the exception is then the diagonal, where I'm multiplying row vectors or taking the inner product of a row vector with itself. And there I'm just taking as many ones as there are in that row, and that's exactly the degree. So it's not too difficult to convince yourself that this is what you're getting. And this matrix has a special name as well. It's called the signless Laplacian. It's obtained by taking the degree matrix and adding the adjacency matrix. Now, if we're talking about signless matrix, there should also be one with signs, and that's this matrix here, where instead of a plus, you take a minus. And this matrix is then called the combinatorial Laplacian. There is also probabilistic Laplacian that plays a role for certain applications, but I'm not going to mention that in this lecture at least. So you see along the diagonal, you have precisely the vertex degrees, 2, 3, 2, 3. So 2 edges, 3 edges, 2 edges, 3 edges incident. And otherwise you have minuses where there was a 1 in the adjacency matrix and zeros everywhere else. The signless is exactly the same, but with pluses everywhere. So no negative signs there. The combinatorial Laplacian is somewhat more popular. It has more nice properties than the signless Laplacian, but of course there is also significant research around properties of the signless Laplacian. And one feature that will be important later on, for instance, is that in the Laplacian matrix, all the row sums and all the column sums are 0, because you have exactly as many -1s in each row as the diagonal entry is. So all the row sums are 0, all the column sums are 0, which means, among other things, that it's always a singular matrix. It always has determinant 0. And 1, 1, 1, 1 is always an eigenvector for the eigenvalue 0. And that's kind of useful and important. All right, so now let's define spectra. So this is about spectral graph theory. What do we mean by spectra? Since the adjacency matrix and the Laplacian matrix, among others, are square matrices, it does make sense to look at their eigenvalues. They're even symmetric matrices, so we know for a fact that the eigenvalues are going to be real, because all symmetric matrices have real eigenvalues only. And we even know more. We also know that there is an orthogonal basis of eigenvectors, all with real entries. Both of these properties are very useful indeed. Now, we're talking about spectrum of a graph, often, rather than spectrum of the adjacency matrix of a graph. The reason why we can do that is actually that the eigenvalues do not depend on what adjacency matrix I take. So in the adjacency matrix, I have some choice. I can choose the order of vertices. But it turns out that, at least for the eigenvalues, this order is irrelevant. It doesn't matter which order I take, because if I have a second adjacency matrix with a different vertex, then I can transform to So I can transform between the two adjacency matrices by means of a permutation matrix. So a permutation matrix that simply switches the order of vertices. I can express the one adjacency matrix in terms of the other using this permutation matrix that just permutes the rows and the columns accordingly. But that means that these two are similar matrices. So I get the one by conjugation from the other. I get one by taking some matrix inverse times A times that matrix P. And similar matrices, so that can be obtained by this type of transformation, always have the same spectrum. That's a well-known fact from linear algebra. So they have the same eigenvalues, A prime and A, which means that it doesn't actually matter what order of vertices I took, the eigenvalues I'm getting are always the same. And so it does make sense to say that the spectrum of a graph, when we are referring to the eigenvalues of the adjacency matrix, because it doesn't matter which adjacency matrix we take. We could take any order of vertices and always end up with the same spectrum. And the same works equally well for the eigenvalues of the Laplacian matrix, and we call them the Laplacian spectrum. Again, it's irrelevant what order of vertices we take. Here is a simple example. Again, the same four-vertex graph as before. A reminder what the adjacency matrix and the Laplacian matrix look like. And if you work out the eigenvalues, which is a fairly straightforward exercise, you get these two spectra. The adjacency matrix consists of 0, -1, and two quadratic irrationals, half, 1, plus minus root 17. The Laplacian spectrum in this particular case consists of four integers, 0, 2, 4, 4. It doesn't always have to be in integers by any means. However, one thing that we do know, and I'll get back to that later, is that 0 always occurs in the Laplacian spectrum. So this last one here should never come as a surprise. Generally, adjacency spectrum and Laplacian spectrum are not related in any particular way, but if the graph is regular, so if all the vertices have the same degree, then we have a very simple, straightforward connection between Laplacian and adjacency matrix. The diagonal entries are then all the same, they're equal to R. So we can write the Laplacian matrix like this, Ri minus A, and it follows that the eigenvalues are related in a very simple way. If the eigenvalues of the adjacency matrix alpha 1 to alpha n, then the Laplacian eigenvalues are simply R minus alpha 1, R minus alpha 2, and so on up to R minus alpha n. It's a very simple transformation. In general, there is no such simple formula like this one. This only works if my graph is regular. So having the notion of eigenvalues and the notion of spectrum of a graph, it might be interesting to have a look at some special graphs and to get a feeling of what the eigenvalues of graphs might be, what kind of things to expect. The simplest possible graph in some sense is the edgeless graph, which has no edges whatsoever. All the entries of the adjacency matrix are 0. All the entries of the Laplacian matrix are 0. So 0 is the only eigenvalue. It has multiplicity n. Rather boring. It gets a little bit more interesting with the complete graph. So graph where all the edges are present, and then all the entries in the adjacency matrix are equal to 1, except for the diagonal entries, which are equal to 0. It's only slightly more complicated because, well, if you look at it, if you add the identity matrix I, then the diagonal fills up and you're getting a matrix where all the entries are 1 and the rank is 1 because all the row vectors are just the same. So you only have rank 1. And that in turn means that you have n minus 1 linearly independent eigenvectors, all for the eigenvalue minus 1. And the last remaining eigenvalue is then n minus 1. You can easily convince yourself that the 1, 1, 1, 1, 1 vector is an eigenvector for the eigenvalue n minus 1. And that's that. Got minus 1 with multiplicity n minus 1 and n minus 1 as a simple eigenvalue for the complete graph. For the Laplacian matrix, we can actually convert because the complete graph is regular. We have the eigenvalues n with multiplicity n minus 1 and 0. This gets me to the first problem. So to tell you what this is about, you know that there will be a problem session later at 5 o'clock South African time, so half an hour after the end of my presentation. And in that session, some problems will be discussed. And the idea that we had was that I would present these problems now as part of my lecture. So you have some time and opportunity to think about them, either right now during the lecture or later during the break. And then in the second part of the day, you will see solutions of these problems. And the first problem is a rather natural one. If we know complete graphs, another natural type of graphs to look at is perhaps the complete bipartite graph, KAB. So we have A vertices on one side, B vertices on the other, all possible edges in between. So the question here is, what is the spectrum of the complete bipartite graph KAB? And what is the Laplacian spectrum of KAB? Can we determine those as well? Uses similar ideas to the complete graph, maybe a little bit more involved. Okay, so more about that in part 2 of today, where Kenneth will tell you about the solutions to these problems. Here's another special case that one might be interested in, the path and the cycle. I didn't mean path and star here. Okay, so first typo identified. The characteristic polynomial of the path and the cycle are related to the Chebyshev polynomials. And one can use that to prove that the eigenvalues of the path can be expressed as these cosines, and the eigenvalues of the cycle as well, just with slightly different numerator and denominator here. In particular, because the cosine is between -1 and 1, the eigenvalues of the path and the cycle are all between -2 and 2, which is actually a rather special property. There are not so many graphs that do this. All right. So to show that, one first works out the characteristic polynomial, basically, and one can relate it to the famous Chebyshev polynomials. And then this comes out of the calculation, basically, which I will not show, just as another example. So next one might wonder what happens if graphs are manipulated in one way or the other, if you perform operations on graphs. And in many cases, the effect of graph operations on the spectrum can be described. So you can say exactly, if you perform this type of operation, this and that will happen to the spectrum. In some cases more explicitly than in others. The simplest example is probably the disjoint union. So you take two graphs that are disjoint and you just put them together, form the disjoint union. Then if you choose an appropriate ordering of the vertices, the adjacency matrix of G1 will form one block, the adjacency matrix of G2 will form the other block, and there will just be zeros everywhere else because there are no edges going between G1 and G2. So if you choose the ordering of the vertices in such a way that G1 comes first and then G2, then the matrix will look like this. And it's quite well known that if you have such a block diagonal shape, then the spectrum is just the union of the spectrum of the matrix here and the spectrum of the matrix there. So what you get is just the spectrum of G1, the spectrum of G2. You put them together, the multiplicities get added up, and that's that. And the same works for the Laplacian. So knowing, for example, the spectrum of complete graphs, we would now be able to say what the spectrum of the union of complete graphs is. And yeah, later today you will hear Kenneth say a little bit more in this direction. This takes me to problem number 2. Another example of a graph operation that one can perform, where one has a nice result on the spectrum. It's slightly more complicated than the disjoint union, certainly, but still quite doable. If we take the Laplacian matrix of an invertex graph, then 0 is always one of the eigenvalues. We know that for sure. I told you that before. And then we have some other eigenvalues, lambda 2 to lambda a. So it turns out if you take the complement, which means you put an edge where there is no edge in G and the other way around, then the new graph has eigenvalues also 0. It has to have 0 as an eigenvalue, but the others are just n minus lambda 2, n minus lambda 3, and so forth, up to n minus lambda a. So under the complement construction, we have a very nice result about the Laplacian eigenvalues. Not so much for the eigenvalues of the adjacency matrix. If the graph is regular, then there is a nice result. Otherwise, it's not quite as nice. All right. So for the complement, where edges are replaced by non-edges and non-edges by edges, we can say something nice about the Laplacian spectrum. And there are other examples of graph operations where one can say something about the spectrum. For example, our Cartesian products. All right. One more tool that is often useful in spectral graph theory is something from linear algebra. It's the Perron-Frobenius theorem. It's an old and classical theorem, but maybe not so well known. So if you have a matrix with non-negative entries, that's crucial, non-negative real entries, then it turns out that there is always a positive eigenvalue that's also the largest of all the eigenvalue in the absolute sense. Right? So generally speaking, the greatest absolute value of an eigenvalue of a matrix doesn't have to be an eigenvalue itself, because the largest eigenvalue in absolute value could be negative, it could even be complex. But if you have real non-negative entries, then you know for a fact that the spectral radius, the greatest absolute value of an eigenvalue, is in the spectrum itself. And it has a positive eigenvector. So one can even say a bit more. If you have any non-zero vector with non-negative entries, and an inequality like this holds, so not an equality like in the eigenvalue equation. If you have an inequality, then that already implies that lambda here can at most be equal to the spectral radius. And also, if you have equality here, so if lambda is the spectral radius, then x must, if lambda is the spectral radius, then the inequality here actually implies equality, so x must be an eigenvector. And in particular, we know that for this largest eigenvalue that must be positive, there is also an eigenvector with positive entries. And one can say something more still. One needs to define first what it means to be irreducible. Basically, you associate a graph with the matrix where you put a directed edge, an oriented edge from a vertex to the other, if and only if the corresponding entry is positive. And if the directed graph you get in this way is strongly connected, so you can go from any vertex to any other along the directed edges, then the matrix is called irreducible. In this case, rho is necessarily a simple eigenvalue, so it's an eigenvalue of multiplicity 1, and there is a positive eigenvector. And this is the case whenever, definitely the case whenever G is connected. So then the adjacent matrix is irreducible. So that then tells us that spectral radius is a simple eigenvalue. It always has multiplicity 1. I will come back to the spectral radius later in my presentation. It is one of the most important spectral parameters associated with a graph, and there is lots of research on it. The Perron-Frobenius theorem basically tells us that in connected graphs, there is always one largest eigenvalue, and that's positive, and it has multiplicity 1, and it has a positive associated eigenvector, all of which are nice properties. Speaking of properties, so special properties of a graph can often be seen in the spectrum as well. So the spectrum is something that's purely algebraic. It's basically an algebra, but somehow magically, looking at the spectrum, you can often infer information about the graph without looking at it. So if I just tell you the spectrum, or more specifically the Laplacian spectrum, you will be able to say whether or not the graph is connected. And that's a result of this theorem, which tells us that the Laplacian eigenvalues are always non-negative. We saw that in the example. 0 is always an eigenvalue, but more than that, if G is connected, then 0 is a simple eigenvalue. It's got multiplicity 1, and generally the multiplicity of 0 as an eigenvalue is precisely the number of connected components. So if you look at the Laplacian spectrum, you can just count the zeros, and that tells you how many connected components there are. In particular, if there is only one zero, you know the graph is connected. Now, why is that? So first of all, the 1, 1, 1, 1 vector is an eigenvector for the eigenvalue 0. I told you that before. That's got to do with the fact that the row sums are all 0 by definition in Laplacian. And if we take any eigenvector for some eigenvalue lambda, then, well, we can perform some manipulations with that. We can always assume that at least one of the entries is positive, because we know that the eigenvectors can be chosen real, so all real entries, and they're non-zero vectors. So if it happens that all the non-zero entries are negative, well, then we just take minus the vector, and we've got another eigenvector which has positive entries. So we can assume that at least one entry is positive, and we can pick the largest positive entry. By the definition of the Laplacian, we then get this here from the eigenvalue equation. These xj are entries of the eigenvector, so they're at most equal to xi, the largest entry. So we've got this inequality. And then in this sum, xi now occurs exactly as often as vj has neighbors. And that's precisely the degree. So xi occurs exactly degree of vi often here in the sum, which means these guys cancel and I'm getting 0. So reading the inequality out, I've got lambda times xi greater than or equal to 0. And since xi was positive, I know that lambda cannot be negative. So all the eigenvalues are non-negative. We know that lambda is greater than or equal to 0, and if it's equal to 0, then here in this inequality, we must have equality. And what did we do there? Well, we said the xj are at most equal to xi. For equality to hold, all the xj have to be exactly equal to xi. So that means that all the neighbors are adjacent to vi. So all the neighbors of vi have the same value xi associated with it in the vector. Then I can play the game again with the neighbors of vi. So the entry associated to vi is the same as the entry in the neighbors, is the same as the entry in the neighbors of the neighbors, and so on. And so in this way, I can spread out across the entire graph, at least if the graph is connected, by just iterating this idea. And I find that, in fact, all the entries of my vector must be equal to xi. So the only eigenvector associated with the eigenvalue 0 is, in fact, 1111 times some constant. So there's only one eigenvector for eigenvalue 0 if G is connected up to multiplication, which is the vector where all the entries are the same. And so in a connected graph, the multiplicity of 0 is just 1. And for the general case where I have single connected components, I can just apply the result on disjoint unions, because then my graph is the disjoint union of connected components, and the spectra are just added up, or taking the union of the spectrum. Moving on. Another property that is nice in graphs, and that one might be interested in, is bipartiteness. So is a graph bipartite or not? I see something coming up in chat. It's a very, very long. Okay.
Sorry, Stephan, it's meant for someone else.
Yes, I saw it. Cheers to Paul. All right. So bipartiteness is a relevant property. And we can detect it from the spectrum as well. So here we can take the spectrum of the adjacency matrix. And it turns out that we can determine from the spectrum whether or not the graph is bipartite. And that's because of this theorem. So if a graph is bipartite, then the spectrum is symmetric. So if alpha is an eigenvalue, then minus alpha is, and the other way around, and they have the same multiplicity. And the proof is really just a calculation. If the graph is bipartite, then its adjacency matrix can be expressed like this. So I first have the one partite class and then the other partite class. I pick the appropriate ordering for that. And the adjacency matrix will look like this. There are all zeros here for the one partite class, all zeros down there. That's the other part of the graph. But there are no edges between graphs in the same class. So there are all zeros here and here. And there are some matrix here and its transpose over there. Now, if we let X be an eigenvector for some eigenvalue alpha, we can split it into the two parts of the graph. And we have some matrix equations. The eigenvalue equation becomes m times x2 must be equal to alpha times x1, and then transpose times x1 must be alpha times x2. Then we introduce some minuses here and here. Very basic manipulation, and then we can get back to an equation for the original matrix, the vector where I'm keeping some of the entries and make all the others negative. That's also then an eigenvector, and it's an eigenvector for the eigenvalue minus alpha. So this shows that minus alpha is an eigenvalue, and because the eigenvectors directly correspond to each other, the multiplicities are also the same. So we can if a graph is bipartite, we notice it somehow in the spectrum. And in fact, it turns out the converse is also true. If the spectrum is symmetric, then without knowing anything else, we do know that the graph must be bipartite. I can say even a bit more. If rho is the spectral radius of a connected graph and minus rho is also an eigenvalue, then that's already enough to be bipartite. I don't even have to somehow know full symmetry. It's good enough if I know that the smallest eigenvalue is minus the largest, basically, in a connected graph. And then that's already sufficient to know that the graph is bipartite. This is problem 3. You will hear its solution later today when it's Kenneth's turn. All right. So next, I want to talk a little bit about spectrum and combinatorial aspects. Here, I'm interested in the question, what does the spectrum have to do with combinatorial questions that I can ask about? So graph, specifically questions of enumerating certain things, counting things. A very basic instance is counting walks. Now, a walk of length r is just a sequence of vertices. They don't have to be distinct. So this is maybe a difference from a path in a graph. In a path, you usually assume that you're just walking along distinct vertices. You're never getting back to the same vertex again. But in a walk, you're explicitly allowed that. So you can come back to the same vertex repeatedly. It's fine, as long as with each step, you're going from a vertex to an adjacent vertex. But walks can be arbitrarily long, because you're allowed to repeat vertices. Now, it turns out that the number of walks of length r that take you from a vertex vi to a vertex vj, that can be obtained from powers of the adjacency matrix. Specifically, if you take the rth power of the adjacency matrix and then look at the ith row and jth column, then that tells you how many walks there are from vertex I to vertex j that take precisely r steps. Proof is simply by induction on r. You can start with r equal to 0, or if you prefer, if this kind of sounds a bit dodgy, because you don't like walks of length 0, you can start with r equal to 1, and it makes as much sense. But so when r is 0, we can just say that walks of length 0 mean I start at the vertex and then I stay there, I do nothing. In which case there is one walk of length 0 for each vertex, and 0 walks between any two vertices of length 0, because in 0 steps I can't get from anywhere to somewhere else. And that's precisely then the identity matrix. So it's adjacency matrix to the power 0, which is the identity matrix as it should be. And then for the induction step, you simply note that every walk of length r can be broken up into the walk of length r minus 1 up to the second to last vertex, and then a final jump from the second to last vertex to the last. And of course, the second to last vertex and the last vertex have to be adjacent. So we can do it like this. The number of walks from vertex I to vertex j that take length r can be obtained by summing over all possible vertices vk that can be second to last. It must be a neighbor of vj, of course, because I have to be able to make the final step. The sum of that, or over that, of the number of walks from vertex I to vertex k of length r minus 1. And well, I can express this as the sum over k, this wik r minus 1, which is the entry in the r minus 1th power of the adjacency matrix by the induction hypothesis, times the entry of the adjacency matrix that corresponds to row k column j. And that is 1 if this condition is satisfied, and otherwise it's 0. So that's precisely then the matrix product of the r minus 1th power of A and A itself. And I'm complete with my induction step. I've shown that walks of length r can be counted by the entries of the rth power of the adjacency matrix. Relating it further to the spectrum, we can look at closed walks. That's just walks where the first and the last vertex are the same. You start at the vertex, you walk around the graph, and at the end you come back to the exact same vertex. That's called a closed walk. And we can relate them to the spectrum with a rather elegant formula, at least elegant in my view. If you know the eigenvalues of a graph, then you can count the number of closed walks of length r by taking the sum of the rth power of all the eigenvalues. And that's equivalently the trace of the adjacency matrix to the power of r. Right, let's think a bit about that. Why do we have that formula? Well, the number of closed walks is by definition equal to this sum. The sum counts walks of length r that go from some vertex vk to the vertex itself. Right? Start and end must be the same. This counts how many walks there are that start at vertex k, end at vertex k, and take precisely r steps. Summing all of these, I get precisely the number of closed walks of length r, and that's precisely the diagonal entries in the rth power of the adjacency matrix by what we've seen before. So that's the trace, sum of the diagonal entries. So all we now have to do is to combine some facts from linear algebra, specifically the trace of a matrix is equal to the sum of its eigenvalues. It's a famous result of eigenvalues. And the eigenvalues of an rth power are just the rth powers of the eigenvalues. Combining that, I'm getting exactly the right formula that I was claiming, namely the rth powers of the eigenvalues summed overall. And this is k. That gives me exactly the number of closed walks of length r. So two special cases are sometimes useful. Walks of length 1, well, there are no closed walks of length 1 because in one step you go from a vertex to some other vertex, but you're not getting back. So then you're just getting 0, of course. Walks of length 2, well, you walk along an edge and then you're going straight back. So the number of possibilities to do that is just the number of edges times 2, because you can pick any edge for that, and well, you can start at either end. So that's twice the number of edges. This is just the number of closed walks of length 2. So by what we've shown, this is the sum of the squares of the eigenvalues. It's always equal to twice the number of edges. One can go backwards, and that's often useful. So if one knows something about the number of walks in a graph, then one can infer things about the spectrum. Specifically, one can get the spectral radius by means of a limit. So if a graph is connected and not bipartite, then this limit here exists. So I'm taking the number of walks of length r, the rth root of that, and then the limit. And that turns out to be precisely the spectral radius, as we will see in a moment. If the graph is not bipartite, that's important here. There is a good reason for that, because if the graph is bipartite, then all possible walks all possible closed walks have even length, because I'm always moving between the two partite sets of my bipartite graph. It can only go sort of back and forth. And coming back to the same vertex that we started with is only possible after an even number of steps, which means that in bipartite graphs, this is ultimately zero and non-zero. So if the graph is bipartite, then we have to take this limit instead, where we just take even indices, even length walks. How do we prove that? Well, we take the formula for the number of closed walks of length r, and we can assume that the spectral radius, the largest eigenvalue is the first one, alpha 1. If the graph is connected and not bipartite, then we already know from what I said before that minus rho is not one of the eigenvalues. So then all the other eigenvalues are strictly less in absolute value than rho. So after rewriting a little bit, I have this expression where all these quotients, alpha k over alpha 1, have absolutely value less than 1. So all the terms in the sum are something less than 1 to the power r. If I let r go to infinity, then these all go to 0. So the whole bracket here goes to 1, and the statement then follows quite easily. I just take the nth root, and then the limit is r, the rth root, and then the limit is r goes to infinity. And for bipartite graphs, I can do more or less the same thing, except that now minus rho is one of the eigenvalues, and I have to restrict myself to even values. So it's the same principle. Minus rho is then another eigenvalue. You can say the last one, alpha n, is minus rho. We just consider even lengths then, but otherwise the argument is exactly the same. I've got a 2 here now instead of a 1, because there is now the alpha 1 divided by alpha 1, but also the minus alpha 1 divided by alpha 1, which gives me another 1 here. But all these go to 0, so the bracket goes to 2. And if I take the 2 rth root here, then this part will go to alpha 1, and here I'm taking the 2 rth root of something that goes to 2, so eventually that will converge to 1. And I'm done as well. So this is often useful if one wants to prove things about the spectral radius. Often an indirect way of approaching that is to somehow count walks in your graph. If, for example, you can show that one graph has more closed walks than another graph for any possible length, then because of this connection, you can also say that the one has greater spectral radius than the other. And that is useful. Okay. The characteristic polynomials are another instance where we have a nice connection to combinatorial problems, to counting problems, because it turns out that the coefficients of the characteristic polynomial of both the adjacency matrix and the Laplacian matrix have combinatorial interpretations. So the coefficients are not just arbitrary numbers, they actually mean something in the graph. Let's start with the characteristic polynomial of the adjacency matrix. And there is an old theorem that characterizes the coefficients that occur in the characteristic polynomial that's due to Sachs from 1964. I define the notion of a Sachs graph. It's a graph where all the connected components are either single edges or they might be cycles. And for a given graph G, we define this set of all its Sachs subgraphs. They are not necessarily induced. So there's any graphs where the vertex set is a subset and the edge set is a subset, and this property is satisfied. So the connected components are either single edges or cycles. And then I need some notation, the number of components in H and the number of components that are cycles in H. And with all that, I can express the characteristic polynomial, which is this determinant x times the identity minus adjacency matrix, and express it as a sum over these subgraphs where each contributes a certain term, plus or minus sign, depending on whether it's an odd or even number of components. A 2 for each cycle, so 2 to the power number of cycles. And then the exponent of x here is n minus how many vertices h has. The empty graph is allowed here as well. So the empty graph h, which has no vertices and no edges at all, is part of that set. So one term here is always the one where h has cardinality 0, c is 0, w is 0. So there is always an x to the n, as it should be. How does one get to that? The key idea is to apply the Leibniz formula for the determinant. Now, if you haven't seen this before, you have to believe me that this formula for the determinant holds. It expresses the determinant as a sum over permutations. Each permutation has a sign attached to it, +1 or -1. For each permutation, I get a product of entries. So if my permutation, so if let's say I take a permutation of the numbers 1, 2, 3, and the permutation is 3, 1, 2, then this product would be entry in the first row, third column times second row, first column times third row, second column. So the columns are taken from the permutations, from the permutation, and the rows are just 1, 2, 3 up to n. So this way one can express the determinant for any matrix. And for the characteristic polynomial, the matrix in question is x times I minus adjacency. So the diagonal entries there are just x. And all the others are -1 or 0, depending on whether I have adjacent vertices or not. So this product is 0 whenever I have one of these factors. And that's kind of important. So the cycles of a permutation pi that would contribute something here that's not 0, they have to correspond to actual cycles in the graph. So they can correspond to single vertices, they can correspond to edges if they have length 2, or they can correspond to cycles if it's length 3 or more. But if that's not the case for a certain permutation pi, that the cycles of the permutation do not correspond to cycles in the graph like this, then some entries here in this product are 0 and I have no contribution, basically. So that way I have a correspondence between permutations and these subgraphs, and one can exploit that to get to the formula. So as a consequence, I can express the coefficient of x to the k in the characteristic polynomial like this as a sum of subgraphs of a certain size, with some plus minus terms and some 2 to the power number of cycles. There is a nice special case of this. If the graph doesn't have any cycles, well then the subgraphs are rather restricted because all their components have to be either edges or cycles in the graph. There are no cycles, so the subgraphs are precisely then collections of edges, and the edges have to be disjoint, so they have to form a matching. That's the only subgraphs that there are in an acyclic graph. And then, plugging in, basically, one obtains a nice little corollary that if a graph is a forest, so all its components are trees, then the entries, the coefficients here in the characteristic polynomial count precisely how many matchings there are with exactly k edges. So when k is 0, there is only one 0 edge matching, that's the empty set. So there is always an x to the n. Then the next one where k is 1, well, how many matchings with one edge are there? Well, as many as there are edges, and so on. So one can say very nicely what the coefficients in the characteristic polynomial are if the graph is a forest. They are precisely counting matchings in the graph. There is a similar theorem also for the Laplacian matrix. One can also interpret the coefficients in the characteristic polynomial of the Laplacian. One needs to define what is called rooted spanning forests for that. So a spanning forest of a graph is a spanning subgraph. It has to contain all the vertices. And at the same time, it must be a forest. So there can't be any cycles in it. And in a rooted spanning forest, each of the connected components needs to have a root, some distinguished vertex. So for each of the connected components, we fix one root. The number of ways to turn a spanning forest into a rooted spanning forest is simply the product of the component sizes. Because for each component, I have as many choices for a root as there are vertices. So the total number of choices is then just the product over all the components. And as it turns out, this is also from the 60s, the number of rooted spanning forests of G with exactly K components tell us the coefficients in the characteristic polynomial of the Laplacian. And this is true for any graph, not just for acyclic graphs. So Rk of G, the coefficient that comes with x to k, is up to sign exactly the number of rooted spanning forests with exactly k components. So in particular, in case 0, there is no coefficient here because there is no spanning forest with 0 components. And that's consistent with 0 being an eigenvalue. There is no constant term in the polynomial, and that means precisely that x equal to 0 is one of the zeros of the thing. Right. As maybe an interesting side note, this result appeared in an article collection with the interesting title "Cybernetics in the Service of Communism." I'm not entirely sure what the use of this formula is for communism, but certainly it's been a very, very useful result for spectral graph theory. We get one special case that is very nice and interesting as well, which is spanning trees, spanning forest with precisely one component. Now, in a spanning tree, I have just one component, and the number of ways to choose a root is just the number of vertices. So the number of spanning forests with one component is equal to the number of spanning trees times n, the number of vertices. So we're getting a very simple corollary. The number of spanning trees occurs up to a factor n as the coefficient of x in the characteristic polynomial. So in particular, the number of spanning trees is 0 if and only if the coefficient of x is 0. And that's equivalent to the multiplicity of 0 as an eigenvalue being more than 1. So there is another way of seeing that connectedness means that 0 is an eigenvalue of multiplicity 1. This graph is connected if and only if it has no spanning trees. If and only if it has spanning trees. As another consequence of that, we can express the number of spanning trees in terms of the Laplacian eigenvalues. So we take the Laplacian eigenvalues, let's say the last one is 0. Now we take the product of all the others and then divide that by the number of vertices, and that is then precisely the number of spanning trees for every graph, which is a nice connection also between the spectrum and a combinatorial problem, namely the problem of determining the number of spanning trees of a graph. And again, this number is 0 if and only if there is another 0 factor here. So again, we have this connection. Disconnected if and only if there is another eigenvalue 0. One more corollary of this result on the Laplacian characteristic polynomial concerns the Wiener index. So those of you who were here yesterday and who saw Peter Ankelmann's lecture will certainly remember the Wiener index. The Wiener index of a graph is the sum of the distances between all the pairs of vertices So between any two vertices, you take the distance and you take the sum of all these distances. And surprisingly, there is some connection to the spectrum here as well. Theorem first proved by Meris in 1989, but there are several articles that contain this and equivalent or more general results. So if you have a tree with n vertices and you take its Laplacian eigenvalues, with the last one again being 0, then you can express the Wiener index of the tree in terms of these Laplacian eigenvalues. You take the reciprocals of all the non-zero eigenvalues, so all but the last one, take the sum of those, and that times n turns out to be the Wiener index. So in particular, it must be an integer, right? Because the Wiener index by definition is an integer. And looking at this expression, it's a priori not at all obvious that it should be. And it turns out that it always is. So this is maybe a surprising little factoid that you can also relate a spectrum to something that's seemingly completely different. And that's got something to do with distances in the graph, more specifically a tree. And the way to get that is that first one applies this Kellman's result on the characteristic polynomial. Then with some short calculation, you showed that the statement is just equivalent to proving that the Wiener index is equal to R2, the number of rooted spanning forests with precisely 2 components. And then it turns out that every spanning forest of a tree is obtained by just removing one edge. And then you turn it into a rooted spanning forest by choosing a root on each side. So that's just the product of the component sizes. But at the same time, if you think about it, this is also the number of times that the edge E occurs on the shortest path, on the path between two vertices. Because that's the number of vertices on one side times the number of vertices on the other side. So both are the same. It's just a product of the component sizes. It's the number of ways of turning T minus E into a rooted spanning forest. It's also the number of times E occurs on the shortest path. So that's the number of times that the edge E contributes to the Wiener index. And that shows at the end of the day that the Wiener index is equal to the number of rooted spanning forests with 2 components in the tree. And then you can apply the Kellman's result. Right. So I've told you a little bit now about properties of the spectrum, how one defines it, how one calculates it, how it relates to properties of the graph. Now, the second part, in some sense, of my presentation will be about 2 specific graph parameters that are defined in terms of the spectrum. The first one will be the graph energy, and the second one will be the spectral radius. And I will tell you a little bit about the kind of results around these graph parameters that people are interested in, that people have been investigating, the kind of results that one obtains, including some more recent problems and even maybe the odd unsolved problem. So, as I said, the first graph parameter I'm looking at is the energy. And that's originally coming from a model in chemistry, the Hückel molecular orbital model. And the history is a little bit complicated because this definition is sort of mathematically elegant, but it's not technically what the original definition was. But sort of this one has become popular, at least in the mathematical community, because of its simplicity. So it's simply defined as the sum of the absolute values of the eigenvalues. Now, how would we interpret that? We know that the sum of the eigenvalues is 0. So on average, eigenvalues are 0. And the absolute value therefore tells us like how much the eigenvalues deviate from the mean. And this is, in some sense, a total summed deviation from the mean. Let's look at an example, the example from before, where we have already calculated the spectrum. We know these are the eigenvalues. So for the energy, we just sum the absolute value and we get something. So the energy of this graph would be square root of 17 plus 1, which is the sum of the absolute values. Some special cases where we know explicitly what the spectrum is can of course be considered as well. We can immediately get the energy, for example, the edgeless graph, which is simply 0 because all the eigenvalues are 0. For the complete graph, we usually get that it's 2n minus 2. For the path and for the cycle, you can do some calculations and you get some explicit formulas for the energy as well. So they look like this. So that's all good and well, but surely there should be more to it than just working out the value for some spectral graphs. So let's look at some properties. I mean, how interesting a graph parameter is depends in many ways also on its properties. If it has nice and desirable properties, then it's perhaps worth studying. So one property that's certainly nice and useful is that it's additive over components. If I have several connected components, then the energies just add up. And that's a consequence of the fact that I'm just taking the union of the spectra of the different connected components. So the sums of the absolute values simply add up, getting the energy of the whole graph. Other parameters that one would often like to have are not necessarily true for the graph energy. So this one is a little bit of a, maybe not so much a drawback of the energy, but it's something that at least makes certain problems harder. And that's the fact that it's not a monotone invariant. So if I insert edges, the energy doesn't always go up. You might think that, like the edgeless graph is certainly the graph which has the lowest energy, which is 0. You can't get lower than that. So you would imagine, okay, if you add edges, then maybe gradually the energy goes up. But this is not always true. There are counterexamples, like this one, right? If I take the cycle of length 6, then I introduce an edge there, then somehow the energy goes down. So it's not a monotone property, as opposed to many other properties, if you think about it. So for example, distances in the graph, they're monotone. If you add edges, the distances can only go down. They can never go up. They can only ever go in one direction. The chromatic number is a nice example. If you add edges, it can only get harder to color it. So the chromatic number can go up. It can never go down that way. On the other hand, the independence number would necessarily go down if you add edges, because it becomes harder to find independent sets when you add edges. So these are monotone variants, but the graph energy is not. Here's a really pretty, or well, not sure, I mean, pretty beauty is in the eye of the beholder, but here's maybe some unexpected property of the energy, and that's this integral formula. So you can somehow express it as an integral involving the characteristic polynomial. And there are different versions of this so-called Coulson integral, where you always have the characteristic polynomial involved in some way, and you take some integral, usually integral from 0 to infinity in one way or the other. And somehow magically this becomes the sum of the absolute values of the eigenvalues, which at first glance is, I think, not obvious at all. But of course one can prove it. So the first step is to show some basic integrals. So you can prove this using integration by parts. You can give this to your students in the first year calculus class. If you want to give them a nice challenge, try to prove this. And then once you've got that, you can take the characteristic polynomial, rewrite this expression a little bit. So you have the factorization, of course, involving the eigenvalues. Take the factorization, plug in I minus x, rewrite a little bit. So these two, of course, can be simplified to one factor, 1 over x squared plus alpha j squared. Then after multiplying by x to the 2n, these 1 over x squared disappears, and we've got instead an x squared here. Okay, now looking at this product, this already kind of resembles the thing here. So it remains to take the logarithm, which also turns the product into a sum. So that's certainly good news for us. Product becoming a sum means that the integral that I started out with becomes a sum of integrals of things like this. And we saw earlier that each of these integrals is just the absolute value of alpha j. So I've got exactly the definition of the energy. So putting all everything together, I get the first formula that I was showing you earlier, this one here. And then for the other, you just manipulate a little bit, basically. What one needs there is that the characteristic polynomial has real coefficients, so conjugation can be moved inside the conjugate of the characteristic polynomial at I over g is the characteristic polynomial at minus I over x. And so you can take that and combine that to show that this product is in fact the absolute value here squared. And then you get the second formula out of it. One particularly nice special case of it is if the graph is a forest, because then we know that the characteristic polynomial can be expressed in terms of matchings. And we obtain a nice corollary where the energy is expressed in terms of the matchings of the graph. Right. As always with graph parameters, a question people ask is, well, can we find good bounds? So how large and how small can these parameters be? So how large and how small can the graph energy be if I know something about the graph, like I know how many vertices and how many edges? A very, very early example, and this even came before the actual definition of graph energy in the literature. So before graph energy was defined as a concept, this result was proven. And it's quite a simple bound. It says that the energy is at most the square root of 2 times the number of vertices times the number of edges. Proof is not very hard. What we need to remember is that the sum of the squares of the eigenvalues is equal to twice the number of edges. We saw that earlier. And then we apply the inequality between the arithmetic and the quadratic mean, or if you prefer, the Cauchy-Schwarz formula, the Cauchy-Schwarz inequality. And that tells you that the sum of the absolute values squared is less than or equal to n times the sum of the squared absolute values. This thing in brackets is 2m. So you've got 2m times n, and then we just take square roots on each side and we're done. This bound is not very sharp. So there are cases of equality, but there are not very many. Equality holds for the edgeless graph without any edges, and graphs where all the connected components have exactly 2 vertices. And that's the only ones. But those are very, very special. In the first case, the number of edges is 0, and in the second case, the number of edges is precisely half the number of vertices. But for other values of m and n, the bound is not sharp. The equality doesn't hold. And we will see some improvements. One can also estimate the energy, for example, just in terms of the number of edges. As in this theorem here, the energy lies between twice the root of the number of edges and twice the number of edges. So we have this bound, and it is sharp, so both can hold with equality. Again, the proofs are fairly elementary, based on some of the properties we saw earlier. So you take the sum of the eigenvalues, which we know to be 0, square that, split it into the squared eigenvalues and the pairwise products. Sum of the squares we know is 2m. So the sum of pairwise products needs to be minus m for the 2 to cancel out. And then you take the sum of the eigenvalues instead. Again, you take the square, which is the square of the energy. You get the same first term, the squares. And then here, sum of absolute values of pairwise products. And then you just apply the triangle inequality here. This sum is 2m. By what we showed here, the sum inside here is negative m. So then applying the triangle inequality, you get 4m as a bound. Then you take the square root on each side. And then for the upper bound, you can assume that there are no isolated vertices, because if you add isolated vertices, this doesn't change the energy actually. An isolated vertex only gives you an additional eigenvalue 0. So it doesn't change the energy at all. So we can discard all the isolated vertices. But if there are none, then there are at most 2m vertices, most twice the number of edges, and we can use the bound from before, just replace n by 2n, and we get the upper bound. So again, this is a rather simple, these are simple bounds. They are sharp, so there are cases of equality, but generally one can do better. So for if the graph is not very, very special, then one can do better than this. So let me show you one way to improve. In the McClellan bound, we just took the inequality between arithmetic and quadratic mean. And equality holds in that inequality if all the terms are the same. But in the eigenvalues of a graph are basically never all the same in absolute values. So specifically, the spectral radius is usually quite different from all the others. So one way to improve is to split it off and use the fact that the spectral radius is bounded, which we'll actually prove a little bit later. And then using the same approach from the McClellan bound, we get this. The idea being that we apply the inequality between arithmetic and geometric mean as before. Same concept, but we keep the alpha 1 out. The largest eigenvalue is kept out of the sum first. Then we get first the bound like this, and then we look, well, how should alpha 1 be chosen for this to become largest? And some calculus shows that, well, this is the case when alpha 1 is precisely 2m over n. And then the function here attains its maximum. So 2m over n is in a sense the worst case. And we plug that in and get the bound that I claimed before. And this is an intermediate step leading us to a celebrated result about the graph energy known as the Coulomb-Moulton bound. So what did Coulomb-Moulton prove? They proved an upper bound that's valid for every graph with n vertices. So this is now bound in terms of the number of vertices. It's quite simple. It's n half times 1 plus root n. So this is proven in 2 steps. If 2m is less than or equal to n, then we can use the McClellan bound. Then the 2m here can be replaced by n, and n is less than or equal to this, so we're done. And in the other case, we use some calculus again. We consider this as a function of m and look at when is it maximal? When is this largest in terms of m? And it turns out that actually the maximum is for a very specific value of m, which is this, n squared plus n to the 3 half over 4. And then you plug that in and find the upper bound. But of course, equality cannot always hold because, I mean, this, for example, needs to be an integer. And you're taking a square root of n here. So the only hope for this to ever be an integer is that n is the square of a number. And in fact, for equality to hold, you need G to be very special. It needs to be strongly regular, as it turns out. You heard, those who were here on Monday heard about strongly regular graphs. So specifically for this to hold with an equal sign, you need to have a strongly regular graph with these parameters. So k-squared vertices, each of them has this many neighbors, and any 2 adjacent ones have this many neighbors in common. Any 2 non-adjacent vertices have this many neighbors in common. And such graphs exist. It can be shown that there are infinitely many of them, but only if the number of vertices is a square. So for general values of n, it is not known what the precise maximum value is. So when n is a square of an integer, then this is the maximum, but generally it's not always known. But in particular, complete graphs do not have maximum energy. The graph without edges has the least energy, but the graph with all edges does not have greatest energy. So that's maybe curious. So to finish on the energy, let me say something about the energy of trees. So here one can use this integral formula involving matchings. And well, the number of matchings of cardinality 0 is always the same. It's 1. It's just the empty set. Matching of size 1, that's just how many edges there are. That's always n minus 1. And the star doesn't have any other edges. So for a star, all the other m's here are 0. And that's clearly the smallest you can possibly get. So if the coefficients here are smallest, then because everything in here is positive, the energy is also smallest. So as an immediate result, you get that the star has the least energy among all trees, simply because these coefficients, m, t, j, are smallest possible. And on the other hand, we have the path, which is known to have the greatest number of matchings of all cardinalities. So the path has the greatest energy among all the n vertex trees. So star and path are at the two ends when it comes to the energy. That's maybe not surprising because star and path are usually the trees that maximize and minimize everything. But there is a rather neat and elegant way to show that, and that's just using the matchings and this integral formula. There is a lot of research, and I could talk for probably hours on just that aspect, where people have been trying to find maximum, minimum in other similar classes, trees with given restrictions, unicyclic graphs, and so forth. So there is a lot of research, some of which very recent, that has been done on the graph energy. All right, so for my last bit, so I'm trying to spend some time on the spectral radius. I've introduced it earlier. We denoted R of G for the rest of this lecture. So it's the greatest of the eigenvalues. One tool that is useful to analyze, and generally a useful tool in linear algebra, is the Rayleigh quotient. For any symmetric matrix and vector x, you define the Rayleigh quotient like this. And it turns out that the greatest eigenvalue of the matrix can be expressed as the maximum of this quotient over all possible x's. Or if you want to exclude, you can also put a supremum here, but it doesn't matter. The maximum is attained. Just x mustn't be the 0 vector, because otherwise you divide 0 by 0. So in particular, if you take the Rayleigh quotient of some vector x here, then that's less than or equal to the spectral radius, because the spectral radius is the maximum. One can use that to prove things like this one, saying that the spectral radius is monotone. If you remove vertices or edges, then the spectral radius can only go down. And Kenneth later will spend a large part of his session on the spectral radius, so we will focus more on that. And this will be one of the problems he's looking at. Like with the energy, one can bound the spectral radius in different ways. So a simple bound is that the spectral radius is at most the maximum degree, and at least 2m over n, which is actually the average degree. And equality holds in both cases for regular graphs. So for the lower bound, if and only if it's regular; for the upper bound, if and only if one connected component is regular with degree delta. And the way to do that is to consider Rayleigh quotients. Specifically, take the vector all the entries are 1, then you find that the numerator in the Rayleigh quotient is 2m, 2 times the number of edges, because if you take adjacency matrix times all ones vector, then you see that in the matrix product in each row, you're just adding up the ones in the adjacency matrix. So you're adding up as many ones as the degree of the vertex is. So the entries in this product that's simply the degrees of the vertices. And if you multiply by the ones vector from the left, you're just adding all the degrees. The sum of the degrees is twice the number of edges. And in the denominator, you've just got n, because, well, you get 1 plus 1 plus 1 plus 1 n times, and that gives you the lower bound on the Rayleigh quotient. For equality to hold, this ones vector needs to be an eigenvector, and that happens precisely when the graph is regular. For the other direction, with the maximum degree, you take the entries of an eigenvector, choose the maximal entry, and then use an argument that we have used in a similar way earlier with Laplacian eigenvalues, where we proved that they're always non-negative. We find this chain of inequalities, and the degrees are bounded by delta. So after cancelling xi, you get that the spectral radius is at most the maximum degree. For equality to hold, the degrees of all the vertices have to be equal to delta, at least in some connected component. One can prove some other bounds, such as this one. For every graph with maximum degree delta, the spectral radius is at least the square root of the maximum degree. So earlier I said it's at most the maximum degree. On the other hand, it's at least the square root of the maximum degree. So we can bound it in both directions, knowing the maximum degree. I leave this also as a problem for you to think about during the break, and Kenneth later will talk about this. So the very last bit is what can we say about minimum and maximum of the spectral radius for different classes of graphs? Well, minimum and maximum are easy, because I said that if we add edges, the spectral radius goes up, and if we delete edges, it goes down. So the greatest spectral radius is the edgeless graph, 0, and that's the least spectral radius, and the greatest is for the complete graph, and there it's n-1. So generally, the spectral radius is just between these two. But what about other families of graphs? For instance, trees. Again, it turns out that the path and the star are somehow the winners. The path has the lowest spectral radius. Why is that? So we saw earlier what the spectrum is, and this is simply the greatest of the eigenvalues for the path. And for the star, it's the square root of n-1, as one can show relatively easily as well. So and these are in fact the maximum and the minimum. When n is large, this is close to 2, whereas this goes to infinity. So the gap widens. And there are many ways to prove this. There are many different proofs that can be found in the literature. One very nice way that I wanted to show you, or rather that Kenneth wanted to show you because he will do it, is to use this tree operation, which is called the generalized tree shift. What you do is you take some path that doesn't branch out in your tree, and then you sort of cut there, merge the two ends, which is happening here, and put the path there instead. So this is an operation where you take the path and merge its two ends and attach the path to it. This operation is called the generalized tree shift. And as Peter Chikvari showed in 2010, the generalized tree shift increases the number of closed walks of any given length. And earlier I told you that there was this connection between this, the number of closed walks and the spectral radius. So in fact, we can use this generalized tree shift now to prove what I told you about the spectral radius of trees. So specifically, one can show the following, and I leave this also as a problem for later. If I say that T1 is less than T2 in some sense, so if it can be, if I can get T2 from T1 by generalized tree shifts, then one can show that this forms a poset structure where the path and the star are at the two ends. So they are the greatest and the least element. They're the only minimal / maximal elements. And from that one can infer that the path has minimum spectral radius and the star has maximum spectral radius. More about that, as I said, after the break. The very last result I would like to mention is fairly recent, and it had been open for a long time before that. So several decades, I think it was an open conjecture that in planar graphs, the greatest spectral radius is obtained for this graph, the join of a P2 and the Pn-1. So you take a path of length with n-1 vertices and just a path with 2 vertices, and you add all the possible edges between them. So that's the join. And it turns out that among planar graphs, this has the greatest spectral radius. This is a result from 4 years ago, Tate and Tobin. The proof is elementary, but clever. So they are basically proving it in several steps. First, they show that there are two vertices that must have many, many neighbors. That's basically these two. Then one sort of it refines this many to eventually showing that, in fact, they have to be adjacent to everything else, and also to showing that they have to be adjacent to each other, and then that the rest must form a path. This is sort of the steps in which they proceed. The arguments are elementary graph theoretical, but very clever. To conclude my lecture, I would like to thank you all one more time. Thank you very much for joining and for listening to my presentation on spectral graph theory. And I will use this opportunity to shamelessly advertise this book. It appeared about 2 years ago. I wrote it with my friend and collaborator, Wang. It's called Introduction to Chemical Graph Theory. As I told you earlier, the energy is motivated by some applications that originally arose in chemistry. And it's not the only such example. So there is a whole industry around chemical graph theory. It's growing quite a bit. So recently, the AMS, for instance, introduced new AMS codes specifically for chemical graph theory and also for chemical indices. So this is a field that's quite active, and our book aims to introduce people to the field as a whole. A lot of what I presented today is in fact part of one of the chapters in this book. So again, I'm using this opportunity to advertise it. Go buy my book. But thank you one more time. Thanks, Mafunda, for inviting me. Thanks for listening. I'll be happy to answer any questions you might have. And of course, in half an hour, it will be Kenneth to take over.
Thank you so much, Stephan. This was quite an interesting lecture. If you've got any questions, you can post your questions in the chat, or you can ask them directly to Professor Wagner. Maybe I'll leave 1 or 2 minutes and see if we have any questions. Maybe while people are still thinking about their questions, you do define the same concept of energy, but for directed graphs, right?
Oh yeah, there are tons of energies. So, I mean, this is in a way the original energy. The first graph energy was defined, and then people started doing this in all sorts of other contexts, also for other matrices. For example, there is also Laplacian energy. There are energies associated with other graphs. There are energies associated with other counting type questions. So in looking at matching, in looking at energies, we accounted at some point that matchings played a role. So we got this formula here. And well, this is the energy for trees, but in principle, this expression is well defined for arbitrary graphs, but then it's different from the graph energy, and then it's something that's called matching energy. And equally, there is an independence energy and a domination energy. And so people have started generalizing and extending that in all sorts of directions to directed oriented graphs, weighted graphs, and whatnot. So it's a big industry. There is a whole book just about the graph energy, the original graph energy. That's about 1,000 pages long, I believe. And there are other books about energy variance and whatnot. So yeah.
And is there any straightforward relationship between the energy of a graph and a strong orientation of a particular graph? Take a graph and orientation. Is there a particular relationship between those two energies?
Not aware of anything there. I mean, there are certain instances where you introduce orientations. So for example, in that Kellman's result, an important step is to consider orientations of your edges, and then relate the number of trees to certain subdeterminants. But I'm not aware of anything of the kind that you were that you're looking for there.
Okay,
I see there are questions
thank
in
you
the
so
chat.
much.
Is there any simple matrix of order n-1 whose eigenvalues are the same as Laplacian except 0? Not sure. Can't think of any. There are versions of this result that I showed you about the number of spanning trees, where I'm taking the product of the non-zero eigenvalues. Another way to get the number of spanning trees is to remove a row and a column, and then take the determinant of that. And that's then an n by n-1 by n-1 matrix. And the determinant turns out to be the number of spanning trees, basically. But the eigenvalues are not necessarily related in any particular way, except that their product then happens to be the same.
Did you see Brendan's question below you?
Yes, I see Brandon's question. So how intuitively can we think of the graph energy? To be honest, a lot of things are a bit counterintuitive. The thing originally comes, as I said, from a chemical model, and it's got something to do with what is called the pi electron energy, but I don't know enough chemistry to explain that background. But so one interesting thing is that the energy tends to prefer certain cycle lengths over certain others, which is a bit weird. So specifically, if you go from trees, which is the simplest class of connected graphs, to the next level, the next hardest, the next step in order of difficulty perhaps would be unicyclic graphs that have precisely one cycle. And there it turns out that so at the one end you have of course a graph that's more or less like a star, just with an additional edge. But on the other end, things get weird. And it turns out that for the maximum of the energy, you want precisely a cycle of length 6 somehow. And generally speaking, the energy tends to prefer cycles of length that are congruent to 2 modular 4 for some odd reason. Basically, it's got to do with how certain signs are in the formulas, some plus signs and some minus signs, how they appear. And in a way, this could be related to how some 6 cycles occur in actual molecules. But to be honest, this is all not very intuitive. So it's a little bit of a mystery sometimes, why certain things give high energies and certain other things give low energy.
Stephan, I'm going to ask that we answer the remaining questions after the break, just before Dr. Denzi takes his session. Is that fine with you?
Okay, so there are a bunch of other questions, but then okay.
I can see that there's a couple of other questions. Is that fine if we just answer
So
them?
to briefly explain what chemical graph energy is, the answer is no. I don't know enough chemistry, unfortunately. So there is this Huckel orbital model, which I know nothing about. It's a thing, one can look it up online, but not enough chemistry background to say that. Undirected graphs over some classes of rings, I'm not sure I understand it. So, well. Oh, and Odas has posted something. Urban questions on graph energy. So there are plenty. Very good.